Welcome to The Explainer. Today, we're unpacking an absolute masterclass in extreme AI engineering. We are looking at the technical report behind Microsoft's MAI-Thinking-1. But we aren't just looking at a new AI model today. We're actually looking at the meticulous, empirical engine that was used to build it. Microsoft literally calls this their hill-climbing machine. It's this rigorous, system-level optimization framework designed not just to reach a single peak, but to sustain long, relentless, log-linear performance climbs over time. It's a real game-changer.
Okay, let's dive into this. Right out of the gate, Microsoft makes a vehemently contrarian choice here. We're in an era where, honestly, a lot of teams take the shortcut of training their models on the outputs of other smarter models, a process you might know as distillation. But the MAI team, they completely reject it. Their philosophy is that capabilities must be learned, not inherited. Sure, inherited intelligence might be faster to acquire initially, but it completely lacks the steerability and the robustness that's absolutely essential for a model that needs to keep climbing over thousands of training steps. So they chose the harder path, learning from scratch.
Think of this explainer as our own guided tour through a high-tech manufacturing plant. Here's our agenda for the tour. First, the hill-climbing machine. Second, architecting for scale. Third, processing the raw data. Fourth, the data mixing paradox. And finally, number 5, measuring the climb.
Section 1. The hill climbing machine, the core philosophy. Let's start with the foundation and see what rules actually govern this extreme engineering feat.
There are basically 3 core design principles dictating every single decision on this project. First, like we just talked about, no distillation. Capabilities are learned from human knowledge completely from scratch. Second, simplicity is sustainable. They heavily favor clean, scalable recipes and highly transparent infrastructure over quick, unscalable hacks. And third, scientific rigor avoids shortcuts. Every single choice, everything from data mixing to routing algorithms, absolutely must be testable through data-driven scaling ladders, no guessing allowed whatsoever.
Moving on to Section 2, architecting for scale, the machinery. So we know the philosophy, but what does the actual physical machinery under the hood look like?
Now, what's really interesting about this slide is the architecture blueprint itself. Instead of using complex, balanced sparsity everywhere, the team opted for a really clever interleaved design. Notice how they alternate those high sparsity mixture of experts layers, which are the red ones, with simple, dense feed-forward networks, which are the pink ones. This specific layout isn't just about some theoretical performance boost. It's perfectly co-optimized to run with maximum wall clock efficiency on their massive clusters of GPUs.
And you've got to appreciate the scale of this thing. The total model holds a staggering 1 trillion parameters. But because of that interleaved mixture of experts architecture we just saw, it's actually incredibly efficient to run. For any given token of text, the model compresses the data and routes it to just 8 out of the 512 available experts. To put that into perspective, it means that while the model has 1 trillion parameters of stored knowledge, only about 35 billion parameters are active at any one time. It is massive scale, delivered with total surgical precision.
But here's the catch. Routing tokens to 512 different experts creates a massive logistical nightmare. If too many tokens get sent to a single expert, the system bottlenecks and basically crashes like a giant traffic jam. To solve this, the team implemented a dropless routing system to handle high imbalance without dropping any of the data. Plus, really early in training, they initialized the attention layers to exactly 0. Why? Because this prevents the model from collapsing all its representations into a generic mush right at the start. It ensures tokens are distributed cleanly across the experts from day 1.
Section 3, processing the raw data, the fuel. With this massive trillion-parameter engine built, we hit the pre-training phase. The obvious question is, how on earth do you fuel a model this hungry for 30 trillion tokens?
Well, the answer is very carefully and entirely organically. Microsoft explicitly states they use 0 synthetic data generated by language models for pre-training. None. They actively hunt down and scrub AI-generated content from their datasets. So the fuel for MAI-Thinking-1 is exclusively clean, human-generated enterprise-grade data. We're talking web HTML, PDFs, public GitHub code, and academic papers.
But you can't just dump the raw internet into the machine, right? The team actually has an intense, multi-stage obsession with deduplication. First, they extract the HTML. Then they strip out all the boilerplate stuff like navigation bars and footers. And finally, they use these fuzzy hashing algorithms to find near matches. You might be wondering why this level of paranoia? It's because repeating identical data is completely toxic at this scale. If a trillion-parameter model reads the exact same redundant data over and over, its ability to scale up and learn novel concepts just flatlines.
The sheer engineering brute force required here is mapped out in this central decontamination pipeline. Every single source goes through rigorous filtering. They are aggressively, and I mean aggressively, removing common machine learning benchmarks so the model doesn't accidentally memorize the test. If a public evaluation dataset somehow leaked into this pipeline, it would completely ruin the scientific validity of the entire project.
Which brings us to Section 4, the data mixing paradox, the scaling plot twist. Now that we have perfectly clean fuel, we have to mix it.
So the crucial point is how you decide what percentage of math, code, or web text to actually use. Usually, AI researchers just rely on the rank invariance hypothesis. The assumption is pretty straightforward. If you test a data mixture on a small 5 billion parameter model and it does well, then naturally, that exact same mixture will do just as well on a massive trillion parameter model. Makes sense, right? Well, Microsoft found out that this assumption is completely, absolutely wrong.
The data reveals a crazy plot twist. So the team tested two different mixtures, a STEM-heavy mix and a code-heavy mix. At the small 5 billion parameter scale, the STEM-heavy mix was the clear winner, no contest. But check out what happens when they scaled the compute up to a 23 billion parameter run. Halfway through training, the lines actually cross. The code-heavy mix completely overtakes the STEM mix. It's wild.
So why did this happen? It turned out the STEM data was high quality for sure, but it lacked diversity. For a small model, it was great, but as the model scaled up and became way hungrier for novel, complex concepts, that specific STEM data hit a massive wall of diminishing returns. This discovery, which they call rank non-invariance, permanently changed how Microsoft validates data mixtures. They realized you can't just trust small-scale tests anymore. You literally have to test the scaling trajectory itself.
After massive global and local data searches, this is the final optimized 30 trillion token recipe they landed on. Code makes up a huge chunk, 54.6% of the diet. And what's really fascinating here is how they loop the data. High-quality math tokens are apparently so valuable that they are looped an average of 5.28 times. Meanwhile, general web text is so vast and so redundant that they only used about half of what was available. They didn't even exhaust the web text a single time.
Section 5. Measuring the climb. The measuring stick. We've got the engine, we have the perfectly optimized fuel, and we've trained the model. Now, how do we accurately measure it?
Microsoft measures the model using something called negative log likelihood, or NLL. Instead of asking the model to generate some long free-form answer, or, pick A, B, C, or D on a multiple-choice test, NLL strictly measures the model's fundamental, core ability to predict the exact next token given a ground truth prefix.
You might be wondering, why abandon standard generative tests like MMLU or math during pre-training? Simply put, because standard multiple-choice tests are incredibly fragile. A model might actually know the right answer, but fail the test simply because the dataset used a Unix-style newline instead of a Windows-style newline, or maybe it just forgot to wrap its answer in a specific formatting box. NLL strips all that arbitrary formatting noise away and offers a pure, totally unbiased look at the model's raw knowledge.
And this brilliantly illustrates exactly why all this extreme engineering was worth it. When MAI-Thinking-1 finally hit the elite post-training benchmarks, the numbers were just staggering. It achieved a 97% on the AMI 2025 Math Reasoning benchmark. It hit 52.8% on SW Bench Pro for agentic coding. I mean, these are numbers that place this model squarely among the absolute strongest frontier models in the entire world. Let's move to and see how this builds in the final phase. This charts the model during its intense reinforcement learning climb. Because the base model was built with such rigorous, scalable fundamentals, it doesn't just plateau. It sustains long, beautiful, log-linear performance climbs over thousands of training steps. It is quite literally a hill-climbing machine doing exactly what it was engineered to do from day one.
Which leaves us with a truly provocative thought to wrap up on. MAI-Thinking-1 is not just a static product release. It is the very first output of a scientifically rigorous optimization loop. If this is just the beginning of what this infrastructure can do, where exactly is the summit? Thank you so much for joining me on this explainer, and I highly encourage you to keep a close eye on where this machine climbs next.